Chailloux. So I'm going to talk about algorithm to solve the shortest vector problem in a regime where we have low memory. So let me introduce the problem. So we define a lattice by being the set of all integer linear combinations of the vectors of a given basis. For example, here we have B1 and B2, two vectors that form a lattice. And we have some of the lattice vectors represented by black dots. And given this lattice, we have the shortest vector problem that asks us to recover the shortest vector in the lattice. So here's the vector in red. So why are we interested in solving this problem? SVP is an NP-hard problem. It is hard in average and believed to be quantum resistant. So it makes it a good candidate for post-quantum cryptography. There is a lot of problems that derive from SVP and a lot of cryptographic schemes based on these problems. So from a cryptanalytic point of view, all these schemes are broken if we are able to compute a reduced basis of the lattice in efficient time. And there exists an algorithm that computes a reduced basis, and it uses a SVP solver. Excuse me. So the security of this crypto system directly relies on the complexity of solving SVP. That's why it's important to know in which time and with which memory resources we are able to solve SVP to estimate the security of those crypto systems. So first of all, I'm going to present a method to solve SVP by lattice sieving, then an improvement of this method by filtering, and I will introduce our new code for a tailored filtering for the regime we are interested in. And I will apply it to construct a framework to solve the problem and give our complexity results. So first of all, lattice sieving. Sieving is a class of algorithms, of heuristic algorithms, and the main heuristic we use is that we assume that lattice vectors are uniformly random in RD. So it's just a simplification to analyze the complexity of the sieving algorithms. And actually, random vectors of norm-atmos R. So if you consider a ball of radius R and you pick a random vector in this ball, they will be with high probability on the border of the ball. So in fact, they will be on the sphere of radius R. You have to think in high dimensions to have this intuition. So this is the behavior for uniformly random vectors. And in fact, it has been observed that the lattice vectors have the same behavior when they are sufficiently long. So we can also consider that lattice vectors of norm-atmos R are in fact of norm R or almost. So this is the algorithm, the sieving step. So we start with n lattice vectors of norm-atmos R, and we want to compute n lattice vectors which are reduced by a factor gamma. So to solve SVP using this method, we start by initializing a list with n lattice vectors, with n exponential. Then we apply a first iteration of the sieve step, a second one, and we see that just after a polynomial in D with this number of the dimension of the lattice, we see that after a polynomial in D iterations, we can construct list of vectors which are of norm-atmos gamma to the polynomial in the R, which is exponentially lower than the initial radius R. So we can hope that we have found a short vector in this really small sphere. So now we have to describe how we do the sieving step. So the most naive way to do is by checking each pair of vector in the list, and we add to the output list all the difference of x1 and x2 that are sufficiently short. X1 minus x2 is in the lattice if both vectors are in the lattice by definition. And we have this condition of reduction. So if we consider, just to simplify here, that gamma is equal to 1 and both vectors are exactly on the sphere of radius r. We have a reduction, so we have x1 minus x2 shorter than gamma r, if only if their angle is at most p over 3. And this is equivalent to have this constraint on the inner product. In the following, I will prefer this notation. So the previous algorithm was for the 2 sieve. We were searching for pairs of vectors, and we can also consider 3, 4, or k sieve, k vectors with sum together to find shorter vector. And this is the reason why we consider the k sieve. So if you look at the sieving step, we actually need that the n radius lattice vectors are computable from the input vectors. And there is a theorem that gives us the minimal number n we need to have this property. And we see that it the minimal number of vectors in the list decreases with the number of vectors we sum together, so k. And this directly translates itself into a lower memory when k increases. However, we see that the time explodes when we have a high k. So our goal was to try to keep low memory. I mean low, but here still exponential, and to try to reduce the time to make it practical. So another important notion to have good time memory trade-offs is configuration, and this is the definition of configuration. So we consider k tuple x1 to the xk, and we say that it satisfies a given configuration C characterized by element Cij, if and if all the inner products xi and nj is lower than Cij. And in the following, I will say that the configuration is valid if when we sum together the vector of the tuple, we get a shorter vector. So we see that if we are able to solve the configuration problem, so to find all the tuples that satisfy a certain valid configuration, then we just have to sum them together to get short vectors. So we can achieve the sieve step by going through the configuration problem. Just a word about the choice of the configuration. So we can choose a balanced configuration. So the vectors of the tuple are well distributed all over the sphere. And this choice allows to minimize the list size, so it minimizes the memory. But we can choose any valid configuration. And in this case, we will need higher memory, but for some particular configurations, the tuples can be easier to find. So here we have a higher memory but better time, and it is a good way to improve the time-memory trade-offs. So now let's talk about filtering. So a filter is characterized by a center f here on the sphere, and an angle alpha. And here, if we consider the vector x1, it is of angle at most alpha with f, so we say that it is in the filter. And here, x2 is outside the filter. And we associate each filter to a set. So we are able to here add x1 to its filter f. Actually, we add x1 to the set associated to the filter. And there is this really powerful code structures that allow us to generate filters all over the sphere. So I don't enter into the details of the definition of random product code. The most important to understand is that this code generates uniformly distributed code words all over the sphere. You have here the points over the sphere. And for each code word, we consider that it is the center of one filter. And the important thing is that the random product code provides an efficient list decoding algorithm that allow us to decode any vector x on the sphere to find the nearest code words of the code. So here we are able to decode x and to find the 3 nearest code words in green. So to improve the sieving step using this tool, if you remember the 2 sieves, the algorithm was basically for each vector we were searching for a reducing vector within the whole list. And when we add filtering, we begin by generating the filters. Then for each vector, we add them to the nearest filters. And here we search for the reducing vector. So for each vector, we search a reducing one within the filters of the vector, instead of checking the whole list, which is much larger. And we can do this search step classically or quantumly by reverse search. And you can notice that the time complexity have a great improvement when we apply filtering. So in a nutshell, the filtering strategy for the two sieves can be represented like this. So we have x1 in filter f, and we search for a reducing vector with x1. So we search next to in f. However, when we are searching for a configuration of vectors, so here we have 3 vectors and we want to find a balanced configuration, we see that they just don't fit into one filter. So our idea was to construct this object, so a modified random product code in order to have x1. We know it is in the filter f1, and we wanted to recover f2 and f3 also in the code, so that we can find x2 in f2 and x3 in f3, so that the 3 vectors satisfy the configuration. So we have constructed this code, and we wanted to apply it into an algorithm to solve the K-sieve with tailored filtering. So our algorithm is a sieving step. So we start with n lattice vectors, and we want to compute n reduced ones. And our parameters are k, the number of vectors we sum together, and angle alpha for filtering, and the configuration C. So if you remember, we can choose C balanced to minimize the memory, or unbalanced to minimize the time. So we start by constructing the filters. Then we add each vectors to its nearest filter. And then for each tuple filter, so for each f1, f2, f3, and to fk, we want to find all the solutions within this tuple filter, satisfying a certain configuration C. And then we repeat these 2 steps until we have found all the n solutions we need to achieve the sieve step. So here we have the vectors and the filters, and searching for these vectors x1 to xk satisfying C. It's a problem equivalent to searching for these vectors in red y1 to yk satisfying a configuration C prime that just depends on C and alpha. And this problem is much easier to solve than the vectors with than the problem with the x vectors. It's due to the filtering. So in the following, we will search for these y vectors. So this is our simplified framework, and we see that in the second step, we need to have a subroutine find all solution within a tuple filter. So here's just the input-output of this algorithm. So we have the list L1 to Lk, each one associated to F1 to Fk with the Y vectors, and we have a configuration C prime that we will have to find tuples that satisfy this configuration. And I'm going to present this 4 subroutine briefly to see what happens. So here we have L1, L2, and L3, and we want to find vectors Y1, Y2, Y3 in this list, satisfying this configuration on the left. So we start by constructing L12 with Y1 in L1 and Y2 in L2, satisfying the configuration constraints. Then we construct this list with the same ID, and then we merge. So for each pair sharing a same Y1, we check if the Y2 and Y3 have the final configuration constraint. So this is for the time memory trade-off. So without any filtering, we have the light blue dots, which is the algorithm that don't have filtering. The light blue curve have a different kind of filtering, and we see that with our filtering, in the strong blue curve, we have better results than the previous one. So for the fourth sieve, we have this list under all the configuration constraints to satisfy. So here the strategy is to do two separate two sieves and then merge together the lists. And here we have interesting results because our algorithms allow us to recover the complexities of the algorithm without filtering up and down with a black dot. It is a time and memory point for the best classical two-sieve. Because actually choosing the configuration of in our algorithms allows to recover these two algorithms. And you see in the pink curve that they perform better for the low memory. So it's once again the other filtering technique. And from when we add more memory, here we have a better performance there. So just to put everything in the graph. So now let's go quantum. So here we start with lists in quantum superposition. So just here, psi L1, it is the quantum superposition of all the Y1 in the list L1. So what we do here is that we start with all the Y2 in list L2, and we apply the Grover's algorithms in order to construct the quantum state with all the Y2 in L2 satisfying this configuration. We do the same here, and then here to have all these three constraints. And so after this, we have constructed this state. So we just have to measure it to get Y1, Y2, Y3. Then we can recover the latest vectors x1, x2, x3, sum them together and get one reduced vector. So we have to repeat this process in order to get all the solutions within the Tupper filter. So here, above the above curve is the algorithm without filtering. The triangles is the result for the other kind of filtering. And here we see that for the low memory regime, we have better performance. And for the four-sieve, exactly the same strategy. Here we improve the algorithm without filtering, but the other kind of filtering is better. So just to conclude, in this work, we improved the three-sieve trade-offs, and we've got new trade-offs for the four-sieve. And here are some leads for further research if you are interested in these problems. So thank you a lot for your attention. If you have any question, I will be happy to answer.
I don't have to ask whether there are questions. There is a question. Please.
Have you studied the impact, so the practical impact on the security of Kyber, dilithium, or Falcon?
I haven't applied this to the crypto systems themselves, but in that case, it is mainly the best time, the best asymptotic time that matters. Here we are dealing with more practical algorithms, not for the quantum part, but for the classical. So it hasn't been done for now.
Thank you.
Any further comments or questions? And let's thank the speaker again. Thank you very much.